Listen to this quote for a second. OpenAI, Anthropic, and Google have each reported attempts by malicious actors to use their models for offensive cyber tasks, including a state-sponsored campaign. Now, I know that sounds like a headline straight out of a sci-fi thriller, right? But it's not. This is a direct quote from a groundbreaking new research paper released by the AI Security Institute. Major AI labs are literally already seeing their frontier models being tested by threat actors for real-world offensive cyber operations.
So this naturally brings us to what is arguably the most urgent question in cybersecurity right now. Just how good are AI agents at autonomous hacking? I mean, are they just helpful chatbots giving out code snippets, or can they actually autonomously navigate complex networks, steal credentials, and execute full-blown multi-step cyber attacks? We need to separate the science fiction from the scientific fact here.
Welcome to This Explainer. I am so thrilled to take you through this fascinating research. Today, we're going to break down the anatomy of an AI attack. Think of it like a digital heist. We're going to take a journey through 2 simulated target environments where researchers unleashed 7 different frontier AI models just to see exactly what they're capable of. All right, let's dive right in.
Section 1. The Autonomous AI Hacker. Testing frontier models in the wild.
To really put these models to the test, researchers didn't just ask them questions. They built 2 bespoke, highly realistic cyber ranges. Let's compare our 2 target environments. Over on one side, we have the last ones. This is a sprawling 32-step corporate network attack where the ultimate goal is to exfiltrate sensitive data from a lockdown internal database. And on the other side, we have Cooling Tower, which is a 7-step industrial control system attack. The objective there? Pure sabotage. They wanted to see if the AI could disrupt the physical processes of a simulated power plant.
Just look at the sheer density of the challenge mapped out here. This flowchart represents the last one's corporate range. The AI isn't just answering a quick security trivia question, it has to autonomously chain together 32 distinct consecutive steps. You can see the flow. It starts with initial reconnaissance, then it has to move laterally through the network by exploiting authentication flaws like Kerberos misconfigurations. It has to steal browser credentials, execute unauthorized commands using cross-site request forgery, and even reverse engineer Windows service binaries. It's literally a sprawling maze of interconnected vulnerabilities that the AI has to discover and then exploit, completely sequentially.
And then we have the Cooling Tower industrial range, which brilliantly illustrates the contrast. Now, it looks shorter, right? It's only 7 steps, but don't let that fool you. These steps represent massive units of complex work. To succeed here, an attacker has to gain initial web access, establish remote code execution, and then deeply reverse engineer a custom proprietary industrial protocol. All of that just to talk to the programmable logic controllers that actually operate the physical cooling towers. It requires intense, highly specialized knowledge.
Section 2. Hacking the corporate network. Inside the last ones.
Okay, so let's see what happens when we actually unleash the machines. The really crucial point here is how these models were set up. They weren't given some hyper-advanced custom-built hacking scaffolding. Nope. They were just dropped into a standard Kali Linux environment, armed with everyday open-source penetration testing tools. They operated on a simple reason and act, or react paradigm. Essentially, read the terminal, think about what to do next, type a command, and see what happens. And to handle the massive amount of text generated over hours of hacking, the researchers used something called context compaction. Basically, whenever the AI's context window got too full, it was just asked to summarize its own memory of the network topology and the credentials it had stolen so far.
So, under those incredibly basic constraints, the results were honestly staggering. 22. The frontier model Opus 4.6 autonomously completed 22 out of the 32 steps on the corporate range. It successfully navigated the network, stole credentials, escalated its privileges, and even reverse-engineered cryptographic keys. To put that into perspective for you, the researchers estimate that a human expert would need about 14 hours to complete that entire chain. In a single run, the AI autonomously replicated roughly 6 hours of human expert-level hacking.
Section 3. Attacking the power plant. The Cooling Tower range.
So, could the AI shut down the simulated power plant? Well, the short answer is no, but the way it failed is absolutely fascinating. The models largely struggled here, completing a maximum of only 3 out of the 7 steps. But look at these bullet points. The AI completely ignored the path a human would take. A human would have hacked the web interface first. The AI? It skipped that entirely. It instinctively just performed network traffic analysis, directly probed the proprietary machinery protocols, and started fuzzing the system. And in one totally wild instance, the AI actually exploited an unintended, completely unpatched bug in the simulated power plant by brute forcing session identifiers.
It attributed its success to a, quote, magic subfunction code. It didn't even fully understand what it did, but it broke the system anyway.
Section 4. 2 alarming capability trends: compute scaling and generational improvement.
Let's see how all of this builds into the core quantitative data of the paper. The researchers identified 2 distinct compounding trends that define the sheer speed of AI offensive cyber development. Trend 1 is compute scaling. This means simply allowing the AI to think longer, basically spending more tokens on it, reliably increases the number of attack steps it completes. Trend 2 is generational improvement. Newer models are just vastly superior straight out of the box. They extract way more capability per token spent. And when you put these together, they dramatically lower the barrier to entry for threat actors.
Notice the trajectory plotted log linearly here, tracking the average steps completed against the token spent. If you follow the line for Opus 4.6, guiding your eyes up the curve, you'll see there's no observed plateau. Moving from a 10 million token budget to a 100 million token budget yields performance gains of up to 59%. And honestly, the terrifying part, achieving this requires absolutely zero specific technical sophistication from the operator. You literally just pay the AI provider for more tokens, and the AI becomes a better hacker.
Now you might be wondering, how much does that actually cost? $80. Grounding this abstract data in reality, a massive 100 million token autonomous cyber attack attempt using a frontier model costs a mere $80. That is an unprecedented real-world cost-to-capability ratio. For the price of a decent dinner, anyone can unleash an agent that will tirelessly probe a corporate network for hours on end.
And look at how incredibly quickly this is evolving. Notice the clustering here of average steps completed by the model release date. In August 2024, GPT-4o averaged just 1.7 steps. Fast forward 18 months to February 2026, and Opus 4.6 is averaging almost 10 steps at the exact same token budget, with its maximum runs pushing way, way higher. Each successive generation is drastically compounding the threat.
Section 5. Where AI still fails. The limits of the machine.
Now, it's super important to maintain an impartial, factual perspective here. The AI is not omnipotent. This heat map perfectly visualizes where the current bottlenecks actually are. The red zones on the left show consistent success. So this is your early reconnaissance, host discovery, basic web exploitation. But look at that sudden drop-off. Look at those stark white zones starting right around step 13 and 14. This is where the machine intelligence completely hits a brick wall.
So what exactly is happening in those white zones? What trips up a frontier AI model? Currently, the AI fumbles highly complex, specialist tasks. It struggles with NTLM authentication relays, which require coordinating multiple concurrent processes in real time. It completely gets lost trying to manipulate complex CI/CD software deployment pipelines to plant backdoors. And while it can perform some basic analysis, deep reverse engineering and complex cryptographic key recovery still largely require human touch.
Which leads us to probably the most practical takeaway from this entire explainer. While fully autonomous, end-to-end AI hacks aren't quite reliable just yet, the immediate danger lies in human-AI teaming. The real threat is a human operator using these $80 AI agents to automate all the heavy lifting, the tedious reconnaissance, the initial exploitation, the lateral movement, and then only stepping in manually when the machine gets stuck at those complex cryptographic bottlenecks. It dramatically scales up what a single, solitary human hacker can do.
Which leaves us with a pretty provocative thought to chew on. We saw how much the capability jumped in just 18 months. With AI capabilities effectively doubling at a fixed budget, and with models scaling log linearly with compute, how quickly will those white zones on our heat map turn red over the coming months? Seriously, what is the map of the network going to look like next year? Thank you so much for joining me for this explainer. Keep learning and stay curious.